All right, let's talk about limits. Now, you probably saw limits at the end of pre-calculus, but they don't always do a stellar job going through that because it comes right at the end. And your pre-calc teacher may not have even had time to get to limits. So let's go through limits. Calculus, the difference between calculus and algebra is the idea of a limit. That's what makes something calculus. So we've got these three different functions here. All three of these are undefined at x equals 2. If you plug in x equals 2, if you evaluate f of 2, here you'll get 0 over 0. That's undefined. You can't have 0 in the denominator. Here you also get 0 over 0. Here you would just get 1 over 0. Can't have 0 in the denominator. The function's not defined at 0 for all three of these cases. However, the behavior near x equals 2 is different in these three cases. And that's the idea of a limit. So if I'm close to 2, if I'm around in here, what are my function values close to? 1, 2, 3, 4. They're all close to 4. If I were to walk along the graph, so I'm going from left to right. My x values are getting closer to 2. See, I'm right here. I'm at x equals -1. I'm at x equals 0, x equals 1, x equals 1.5, and so forth. What are my y values doing? So when I'm here at this point, at say x equals 1.5, that y value is that 1, 2, 3.5-ish. What are they getting closer to? Looks like they're getting closer to 4. What if I'm coming from this direction? So I'm walking backwards on this curve here. I'm getting closer and closer to when x equals 2, to that empty circle there. My y values are getting closer and closer to 4. Now, they never actually reach it, but I don't care. I don't care what happens when I get there. I'm not allowed to get there. I'm not allowed to plug 2 into this function. But as I get closer to 2, the y values are getting closer to 4. That's what we call a limit. In this graph, something different happens. Here, all my y values over here are -1. So when I'm at this x value, y is -1. When I'm here, -1, -1, -1, -1. When I'm coming from this direction, though, so when I'm at this point, my y value is at +1. When I'm at this point, my y value +1, +1, +1. That's a completely different scenario than what's going on here. Similarly, in this graph, as I get closer to x equals 2, my y values are getting bigger and bigger, and that's happening from both sides. They're going to infinity. Now, next week, we're going to talk about the formal epsilon delta definition of a limit. And it's pretty cool. I really like the definition of a limit. This is a naive approach here. This is not the mathematically formal definition. By the way, I'm going to save this document that we're looking at now with all my writing on it. I'm going to upload that. It'll be in the announcement with this recording. The version you're looking at right now already exists in one of those modules, but I'll save this one with all my writing on it in the announcement. So you don't have to try to scurry and try to write this down. I'm going to give you this document. So this definition, this naive definition here says, we say that the limit as x approaches a of f of x equals L if, as x gets closer and closer to a, the y values f of x get closer and closer to L. So L is a potential y value. Limits are y values. what y value should be there if the function were continuous. We'll talk about continuity next week. Okay, one way to estimate a limit is just by building an XY chart. Now, this will never prove, you can never prove a limit using these tables we're going to build. These are just to get a gut feeling about what a limit might be. So we got this function here. I'm going to rewrite him down here. F of x is x squared minus 4 over x minus 2. And I'm going to build this XY table. And maybe one or two of these we'll do by hand, but then I'm going to show you how to do this in your calculator. So this is where I'm trying to get. I'm trying to get to x equals 2. Like, you try it. If you tried to do f of 2, you would get 4 minus 4 over 2 minus 2. That's 0 over 0. That's undefined, does not exist. This does not, I know my D and E's will look like 1. That does not say 1. That's a D. D and E does not exist. But what if I plug in numbers close to 2? So maybe I plug in 1, 1.5, 1.9, getting closer and closer to 2. And I've really got to check from both directions. So now I'm going to come in from the other side, maybe 4, 3, 2.5. I could go by smaller chunks. I'm not even being consistent with my change in x here, but that doesn't matter. I could go by smaller and smaller numbers if I wanted to, and I'll show you how to do that on the calculator. Let's see if these y values appear like they're approaching something. So what's f of 1? That would be 1 squared minus 4 over 1 minus 2. Oh, so what is that? Negative 3 over negative 1. I get 3. Okay, what about 1.5? I don't want to do this with my hand, so I'm going to type it in the calculator. Now, I'm going to show you a shortcut here in a minute, but let's type this out long ways. So I want 1.5 squared minus 4, all divided by 1.5 minus 2. 3.5, put that in my table. And I could keep doing this. I could keep just plugging in one at a time, a bunch of numbers. Or here's a couple of shortcuts I could do. I could put this function in my calculator here under y equals. So let me start over and show you what I did. I went here to y equals, and I'm going to type in this guy here. So x squared minus 4 divided by x minus 2. And I need parentheses here. And I look at the graph if I want. I've got some kind of weird window there, so maybe I want to go to a standard window. Now I can actually have it graph or plot one single point at a time if I want. I can go under calc right there. Above trace is calc. I could hit second trace to get the calc and find the value. So I get to plug in x values now. So I could do x equals 1.5. And it not only gives me the y value, but it shows me the point. And I could keep doing that. I got to check on this calculator. Some of them, yeah, see, look, I didn't have to go back and do calc again. Like, it knows I'm going to keep typing in values. So I typed in 2.5. Maybe I want to go, what was that? Next one I had 1.9. 1.9. 3.9. Let me put that in my table there. And I can keep doing that as many times as I want. Or I could go up here, see above window where it says table set. Excuse me. If I go up here, maybe that's where I wanted to go. Let me go to table. Yeah, here. Table set. Yeah. Okay. Sorry. Okay. Yeah, here's how we do it. So we go table set, second window. Tell it our initial X value we want and what we want our change in X to be, what our delta X is. So I don't know, maybe we'll go by 0.3s. We can make that as small as we want. Then I can go second table and it'll just automatically fill in this table for me. So these are all my X values. Here are all my Y values. Excuse me, I've been talking for 4 hours straight. Okay, so we could fill in now all these different X values with these Y values. And we could look at this and see what do we think these Y values are approaching from both sides. Okay, so now we can see as my X's are getting closer and closer to 2, from the bottom, the Y values look like they're going to 4, getting closer to 4. What about from the top? My X's are all bigger than 2, but I'm getting smaller and smaller. The Y values look like they're getting closer to 4. If I wanted to be more precise, I could set that delta X to an even smaller number, maybe 0.001, and maybe I'm starting at 1.99. And we can see at 2, functions undefined. But as the X's are getting closer to 2, the Y values look like they're getting closer to 4. And that'll happen from both sides. So it looks like the limit as X approaches 2 of X squared minus 4 over X minus 2 appears to be, I should say here, seems to equal 4. We haven't proven that. These tables are only good for estimating limits. They never prove it. Okay, let's do the same thing here. Maybe we'll do this one here, sine of X over X. So I would come here, second, Y equals, nope. Y equals, no second. I'm going to turn off this graph. I don't want to look at him anymore. So I can highlight the equal sign that's blacked out there, hit enter, that turned him off. Now I want sine of X over X. I want to make sure I'm in radian mode here. Anytime we're always in radian mode. Let me just say that. All semester long, radians are the natural unit of the universe. You're always in radian mode. So let me check my mode here. I'm in radian mode. Okay. I want the limit as X approaches 0. So I want to be near 0. So I could do my table set here and maybe start at something a little smaller than 0, maybe negative 0.5, and go up by 0.1 at a time, because I want to check on both sides of 0 And now I can go second table and look. So here's from below. I'm less than 0, but getting bigger. The y values look to me like they're getting closer to 1. And then coming from the other direction, I'm bigger than 0, but I'm getting smaller. The y values look like they're getting closer to 1. And we should be able to see that on the graph too. The function's undefined at 0. You can't divide by 0. But as I come in from the left-hand side, the y values appear like they're getting closer to 1. And then when I come from the right, same thing. Okay, so it seems like the limit as x approaches 0 of sine of x over x equals 1. We haven't proven that yet. We're actually going to prove that geometrically next week. Okay, I'll let you guys play with that one later if you want. We can evaluate limits graphically. We don't care what's actually happening at the function value. I want you to note here that if I asked you what is g of -1, what is the actual y value? That's where the solid dot is. That's at 1, 2, 3, 4. That's that spot right there. This is 4. This is a different question. This is really asking not where is the solid dot, but where's the solid dot supposed to be? Because somebody took this graph. We had a pretty nice continuous graph here. Some person came along and plucked a point out and took that point and they moved it up there. This question is asking where'd they move it to? This question asked what was supposed to be there. The answer to a limit is the y value, not the x value. So look at these y values. So I'm getting closer in the 1. I'm writing up this graph here. I'm at x equals -2. I'm at x equals -1. I'm right. Or x equals -1.5. My y value is about 2.8-ish. I'm getting closer and closer. My y values, they're like here, they're here, they're here. They're getting closer and closer to 3. That's if I'm coming this direction. What if I'm writing down? So I'm coming down. Right now, I'm at x equals 2. My y value is about 5. Is that what that was? 1, 2, 3, 4. Yeah. I'm at x equals 1. I'm right here. What's my y value? 4. I'm going down. I'm getting closer and closer to -1. My y value is getting closer to 3. So in this case, the limit as x approaches -1 of g of x is 3. These are different questions. Not all limits exist. If we go back to these very first examples at the top, this limit doesn't exist. The function is not approaching a number. Now we'll talk about these in a minute, infinite limits. But a limit is a number. Infinity is not a number. It says here, approaches a real number L. This graph is not approaching a number. That graph doesn't exist. This graph is approaching 2 different numbers. One number from the left, -1, a different number from the right, +1. This limit would not exist. Limits don't have to exist. This is another example of a limit that doesn't exist because it just oscillates all over the place. So if I were to graph the function y equals sine of 1 over x. You can't see it here, but this graph is oscillating faster and faster and faster. As you zoom in, see it's oscillating, it's going to keep going faster and faster and faster. And the more you zoom in, the closer and closer these are getting. So you can't even, it doesn't even make sense to look at the graph and go, well, where is the graph approaching? As you get closer and closer to x equals 0, you oscillate up and down faster and faster. We can look at table values and we'll see that. So I don't remember what window I got here. So just looking at these numbers, I wouldn't say that looks to me like it's approaching anything. Remember, you can never prove a limit exists using a table. But just looking here, it doesn't even appear that these numbers are approaching anything, because that's a positive number from below. That's a negative number from above. And if we make our delta x even smaller, we'll just get even crazier. We'll get more chaos. This limit does not exist. Now, we're going to learn next time, next class, exactly how to find limits. All the stuff we're doing with tables here is just to get an idea of really to understand what limits mean, to get a conceptual idea of them, and to quickly check what a limit might be. We're going to learn algebraically how to calculate limits next time.